Hello and welcome back to another episode of General Topology, and today we will discuss two important topics. Topic A is connected components of a set, and topic B is the definition of a totally disconnected sets in a general topological spaces. So if we start with the first topic, which is the connected component, the first lemma will talk about what happened if we have a family of connected subspaces, and then we are focusing on taking the union of this family. Well, we want the union to be connected, however, there is be a condition that their intersection must not be empty set. So lemma 1, we can summarize it as the union of a connected set is connected, provided that their intersection is non-empty, which is something, again, as expected. If we think about the open set, we are talking about the union of open set should land to be open. Here is the union of connected set also will be connected, but there is an extra condition that the intersection is not empty. Let's go ahead and we start to prove this one. So what we will do is we will assume the union, which is now, let's imagine it's the union of all those sets, is not connected. Now, if a set is not connected, it has two definitions. First of all, there is a equivalent definition. First of all, there is a closed set, closed and open, non-trivial, proper subset of the space. And the second one, which we will use here, is that my space can be written as A union P, or let's just use another letter than A. Let me just say P union C, with both B and C are two non-empty disjoint sets. So we have two non-empty disjoint sets. If we take the union, they will give me the whole space that I'm considering. Also, because if we look at, they are disjoint and their union is giving me the whole space of the union of AI, B is open and at the same time is closed because it's, as we said, it's global. Now we will use the condition that the intersection is not empty. So I will assume there is an X in the intersection, and that's because the intersection is non-empty. Hence, of course, X will be in every AI, so X must be also in the union, and so it is either in A or in B. Hence, X in B or X in C. Now, without loss of generality, let's say that X is in B. Of course, it is only in one of them, either B or C. It cannot be in both because B and C are disjoint. So we'll assume it is in B. The same proof will go if we assume X is in C. Now, what we will get if we have this, we have this claim that AI intersection B will be equal to AI. Of course, this means that AI will live inside B. That's kind of what we are aiming for. Okay, so the common elements between P and AI exactly as the AI, so everything in P in AI will be in B. Of course, this will give me the contradiction that I'm looking for, because if every AI is subset of P, then the union of AI is subset of B, which means I don't need to use C. That means C is empty because the union will be equal exactly B, but with the union of C is not there, so C must be empty, which is the contradiction I'm looking for. Now, how do we prove this claim? So we prove this claim as follows. We prove this claim as follows. First note that we have is AI intersection B is open set in AI. Why it is open set in the subspace topology? Remember, AI has it is the subspace topology. Well, the reason why, if you remember the open set in the subspace topology, it is always something like this one. It is AI intersection and open set. Now, we know that B is open, so this intersection will be open. Similarly, AI intersection B is closed, because remember we said that the B is also closed. Now we know something that we can use is, but AI is connected. So if we have a connected set, the only closed sets are either empty or AI itself. Of course, this cannot be empty because X lives there. Remember, X lives in AI and also X lives in B. So, hence, AI intersection B is equal to AI, and thus we have B is exactly equal the union of AIs. Why? Because from this one we get that AI is subset of B, and if we take the whole union we'll get it B, which means that C is empty set, which is a contradiction. Because remember, we assume C is non-empty and it gives a partition. Please pause this video, look at the proof again, and think about it. It's a very elegant proof, direct and straightforward. And next, what we'll do next is we will define what is the connected component, which is the part 1 of this lesson. And to define the connected component, we will choose an element A, and then we will look at all the connected set containing A, some of them like this, some of them here, and so on and so forth, some of them like this. And then we will define the connected component to be the union of all those connected set that containing the A. So what we have here is, let X and T be a topological space, the connected component of an element A, and we will denote this by Cx of A, sometimes just C of A, which is the connected component of A, is to define by the union of all connected sets containing A. So we take all the connected set that contain A, and we take the union over all those set. What we will get is a new set. We call it the connected component of A. Now, lemma number 2 will tell me is that this union of all connected set that contains A is again connected. And to see why this is true, we will use the lemma that we just proved, which is lemma number 1, that says that the union of connected set is connected if we have non-empty intersection. Now, why do we have in this case non-empty intersection? We will say by lemma number 1, the connected component of A, which is just the union of all AI. Of course, what is AI? It is AI is connected set containing A. So we take AI connected and A is in AI. This one is connected, and we will write the reason why this is connected. Because first of all, AI is connected, and the intersection of AIs is not empty. Why? Because A itself is in the intersection. So if A is in the intersection, this will be non-empty intersection, and then if we take the union of connected set with non-empty intersection, it will be connected. So this is the first part of the lemma up here, lemma number 2. And so the first information about the connected set, it is a union of connected set, and it will be also connected. Now, this will take me to remark number 3, which we will know more information about the connected set Cx of A. And those information are, first of all, because it is the union of all connected set containing A, it is also the largest. Remember, if we have the union of all the connected sets containing A, of course, what we will get is the largest. Nothing is even larger than this. So here is nothing really to prove, it's just a remark. Remember, if we write it as in symbols, this is the union of all AI, and then we write that AI is connected, and also we write that A itself is in AI. So we have all the connected set that contain A, and of course this will be the largest in terms of subset relation, largest set or largest connected set containing A. Containing A. So this is nothing really we need to talk about it. Now let's look at the second information about the connected set. So now we know it is connected. We know it is the largest connected set containing A. And the third information, it will be even more better. It will be closed set. It is connected and closed. That's a very good properties for the connected components. Now, why it is closed? We will need to use a lemma, which is lemma number 4. So I will just write by lemma 4. Now, what does lemma 4 says? Look, lemma number 4 says the following. In short, it says that if a set is connected, the closure is also gonna be connected. We will come in detail to lemma number 4 next, but for now, all what we need is this information that the closure by lemma 4, the closure of connected set is connected. We will prove it, but for now, let's just use it as is also connected. Okay, that's good news. That's good information for us. The closure of a connected set is also connected. Okay, now, if we look at the closure here of this one, what do we know? What information we know about it will be also connected. And the reason is that CA of X is connected, so the closure is also connected, but also it will contain A. containing A. Now, by remark 3, part A, if you remember, we have Cx of A is the largest one. Now, the closure, of course, may be larger than this one, so they must be equal. So Cx of A closed must equal to Cx of A, which means that the connected component Cx of A is closed. And that's the proof for this lemma here, for this remark. So that's how we do it. Please have a look at this one before we go ahead and we prove lemma number 4. So what we know, what we have learned so far is the connected component is connected, is the largest connected set containing A, and it's closed because the closure will be also connected containing A, so they must be equal. And what we will do next is we will prove lemma number 4. Now we will prove lemma number 4, which is the closure of a connected set is connected. Well, if we assume that the closure is not connected, so we assume the closure of A can be written as B union C, where the intersection between B and C is empty. And as before, we know that B or C, both of them will be global in the closure itself. Because B is open and the complement of B will be C, so it will be also closed. Now, if we take the closure again, so it will be closure of the closure. It will give me the closure of B union C, which is the closure of B union the closure of C, and this is exactly a closure. And this means because B and C is global, this will also give me B union C, which is exactly what we have here, because it's a global. Now, what we know about A is that A can be written as A intersection B union A intersection C, and this is global in A, but A is connected, so A intersection B is empty, and hence we have A intersection C equal to A. A intersection C is A. Or in another word, we can say that A is subset of C. Now, if A is subset of C, the closure of A will be subset of the closure of C. And of course, this cannot be happen. This is a contradiction, because this will lead me to the fact that A equal the closure of C, a contradiction to the fact that B and C are non-empty. Remember, when we separate them, this is, of course, non-empty global sets. And that will give me a proof that the closure of a connected set is also connected. And that's exactly what we want to prove here. And now, next, we will move to totally disconnected. Okay, now we move to part B of the lesson today, and we will talk about totally disconnected spaces. And I think from the name, we can at least have an idea of what type of spaces we are talking about. Totally disconnected, if we just do it geometrically, I would try to have a little bit of geometric. Now, X. Now, if this is a totally disconnected, it means the points are the only one who are connected, because we are saying it's totally disconnected. It's like each point is separated from each other. We cannot have kind of a subset where the points are connected close to each other. So it's kind of the connected sets are only the singleton, and that's exactly the definition that we will talk about in totally disconnected space. So if we just write the formal definition here, we will write that a topological space xt is said to be totally disconnected space if every non-empty connected set so the connected sets, every non-empty connected set is a singleton set. So this will give me the definition for the totally disconnected space. Let's now see one proposition, maybe another formulation for totally disconnected space. And if we connect it to what we already did about the connected component, we see that a space is totally disconnected if and only if the connected component that contains A is just a singleton A, which is kind of makes sense because remember in totally disconnected we said that only connected sets are the singleton, so anything connected will be the singleton. Also the converse is true. If the connected component, which is the largest connected set, is only singleton, of course we expect that there is nothing else, then the space will be totally disconnected. Nevertheless, even the proposition number 5 is easy to understand. We will go over the formal proof. So I will assume we have a space X which is totally disconnected, which means every non-empty connected set is singleton. Now, if we look at our object here, this is the connected component containing A, we know two information in this context. First of all, it is non-empty. The reason why? Because A belongs to this one. Because it's connected component containing A, so it's non-empty. And we know it is connected. And why it is connected, and this is because of lemma number 1. Because lemma number 2. Sorry. Or let's say proposition 2. I think it's proposition 2. So position 2. So we have non-empty, connected, and the space is totally disconnected. Hence, the connected component is a singleton. Now, if it is a singleton set and containing, and because A is already there in this connected component, thus we get Cx of A is just the set exactly A. And that's exactly what we want to prove. And this is the first part of the story, which it really makes sense because this is the only singleton that we have containing the A. Now let's do the opposite. Let's assume that the connected component is only the singleton A, and we prove that any other connected set will be also singleton. So the other direction, assume for every A and X, the connected component containing A, which is the largest connected set containing A, is just a singleton A. Now, let A be any non-empty connected set. We want to show that A is singleton. That's what we want to show. Of course, how to show this one? since we know that A is connected and it is not empty, we can find an element A in A, but the connected component containing this A is the largest connected set containing A. Hence, A must be just part of the set. Now, the connected component is only the singleton. So, A must be also equal to the singleton, and that's exactly what we want to prove, and this is the end of the proof. So we have the connected set is only the connected component that contain the A. Now, what we will do next is we will go over a couple of examples of famous spaces, some of them totally disconnected, some of them not. We know that, for example, the real number is a connected space and it will not be this totally disconnected space. However, if we look at example number 6, we are focusing on the rational numbers, and the rational numbers with the usual Euclidean topology going to be totally disconnected space. Now, how do we going to show this one in this example? Well, this is because if Q is any element in Q, we will focus on the connected component containing Q, which is, as usual, it is all the subset of Q that are connected and they are containing Q. Of course, if we look at this in the number line, just do it here, we will see that for the rational numbers, the rational numbers are between any two rational numbers, we can find irrational numbers, so they are separated by each other. So if we focus on one of them, which is this is Q, and we look at all connected components, the only one that is really rational will be only the singleton. So here we will get just the singleton, which is Q. Remember, this is a closed set, and this is the only closed set containing Q. It's the same as the closure. And for that reason, is singleton. Hence, Q with the usual Euclidean topology is totally disconnected. And that's the proof for example number 6. So at least we see an example of a totally disconnected space. Now, if we look at this example number 7, I would like you to pause a little bit and read this example. So example number 7, and I wrote between two bracket application. I will explain to you why I wrote application, but let's now take a map, continuous map between the real numbers to the rational numbers. If the map is continuous, it will be the constant map. It will be a constant map. Why I ask you to pause and think about it, and why did I write application? Because if you study this in real analysis, the usual real analysis course, the first undergraduate real analysis course, you will find that we also deal with continuous function. This question seems to be solvable using the ideas, or at least the terminologies that we have seen in the real analysis course. So I would like you to pause, think about it, and see if you can solve it using the real analysis technique without using topology or whatever we learned here in this video, and post for me your solution, or at least the idea of the solution, in the comments below. So please pause, think about it. Okay, now we will go ahead and we will solve this application using the technique that we have seen in this video and in general topology course. So first of all, since f of the real number, which is a connected set, will be subset of Q because the image is a Q. Of course, this set up here, let me just change the color here to this one. This set, of course, is connected. Why it is connected? Let me just go ahead and explain to you. So this is connected. Why? The reason, because remember the connected image of a continuous map is connected. So the real number is connected, and the image of a connected set under the continuous map is also connected. Now, if it is connected, by example 6, Q is totally disconnected. So the only connected non-empty set will be the constant, will be the singleton. So f of r will be a singleton. Let me just write it first as this one is singleton. So if we just want to add a little bit more here, by example 6, Q is totally disconnected. Hence, f of r is singleton, and therefore there exists a number C such that f of r is equal to C. Thus, f of x will be always equal to C for all x in R, which means f is a constant function map. And that's the proof. Clean and simple. And please, if you have an idea how to prove this one using the technique that we have seen in a real analysis course, write it in the comments below. Next, we go to example number 8, which we will talk about the indiscrete space with more than one element. And we want to show that this is not totally disconnected. Well, for that, I want to explore the connected component of A. Now, if we explore the connected component of A, this should be the union of all A, where A is connected, and the A is in A. So we take all the connected component. Now, as we said, in our space X, we have A, and we have another element which is B. So if we take the largest connected component, and this is in discrete space, so the only open set is the empty and X, of course this will be X, and of course this will never be the singleton A because X has more than one element in A. Thus, X is not totally disconnected. This is if we talk about the indiscrete. And the final example in this video will be the Sorgenfrey line, which will be totally disconnected. And this is the reason why we don't use it in many examples, because it has some of disadvantages as it's totally disconnected. And to prove this is totally disconnected, we will focus first on the open sets A, B. We'll focus on the set, and we show that these are not connected by all means. Well, if we show that these are not connected, why this will help me to prove what I need to prove is because it will give me that the only connected components are the singleton. Because if any of those intervals are not connected, then the only one that would be connected is the singleton, where A equal to B. Of course, that in the case A equal to B. Okay, so the idea is clear. We only need to prove that those intervals, semi-open intervals, are not connected. So I need to write them as a union of two disjoint sets, and both of those two disjoint sets are open. So what we will do is very easy here. I will write them as this one union this one up here. So I will go from A, B, and if you just can check with me, if we put C here, this is exactly two disjoints. First of all, those are disjoint. This is the first information. Second, non-empty. Of course, A is not equal to B. And the third, which is the most important, are both of them open in the uniform line topology. And of course, this case does not happen in the real number, because in the real number we have open. So if we make this is open, this is not a total partition for the set A and B, and that is the proof for this set as here. I wish you have enjoyed this video about connected component and totally disconnected component. If you have any questions or any comments, please write them down in the comments below, and please don't forget to like and subscribe this video.